Hi, welcome. Let's begin with Rankine cycle. Why is Rankine cycle important? It is used in coal-powered and nuclear-powered turbine power plants. So let's discover the basics of Rankine cycle. Rankine cycle has 4 points. Point 1, 2, 3, and 4. Now you notice at point 1, this is the saturated fluid region, and then there is an isentropic compression. Isentropic means that the entropy remains the same, so S1 equals to S2. After that, you have constant pressure, heat addition, so the temperature jumps from T2 here all the way to T3 over here. So there's a large temperature difference. After that, you would have an isentropic expansion in the turbine. And finally, you will have constant pressure, heat rejection. Okay, so what does isentropic expansion in the turbine mean? It means S3 equals to S4. Simple enough. Okay, and notice, if I zoom in a bit more, location number 4 is not over here. It is not at this SG region. Okay, it's not at the saturated gas region. So that means because it is over here, that means it is not saturated fluid, neither is it saturated gas. Okay, we have to find the ratio for this. So because of that, because this is not the saturated fluid, nor it is the saturated gas region, therefore we need to determine our quality, which is the ratio. So what is our percentage of liquid versus the percentage of the saturation of gas? Okay, this is our X. We will discuss about it and we'll see how it is done later. So let's begin with our question. Let's erase some of these. Example 10.1, the simple ideal Rankine cycle. We have steam power plant operating with the simple Rankine cycle. Simple ideal Rankine cycle, that means the losses are not included and the efficiency of the pump and the turbine are not included. We will see more of this in the next few questions. Steam enters the turbine at 3 megapascal and at 350 degrees, and it's condensed in the condenser at a pressure of 75 kilopascal. Okay, so this is very simple. This is 3 megapascal. Meanwhile, this is 75 kilopascal. This 3 is 350 degrees Celsius. Okay, so this is what the question gives us. So what we can do is we can find our saturation temperature at 75 kilopascal. Okay, that is something we can find. We can also find our S1, our entropy, we can also find our H1, our enthalpy, which is HF and SF. And we can also find our, for location 3, we can find our S3, our entropy at 3, and our enthalpy at 3, H3. Okay, so let's begin to find H1 first. What is our temperature at that location? We can look at table A5. Table A5, saturated water pressure table. We scroll down to 75. So at 75 kilopascal, your saturated temperature is 91.76 degrees Celsius. Let's notate that. 91.76 degrees Celsius. Okay. So what I like to do is, because we have 4 points, we will then write in 4 different columns. So T1, T2, T3, T4, P1, P2, P3, P4, S1, S2, S3, S4, and H1, H2, H3, H4. So this is really useful because when we start to dive into the questions more, we will have so many values and we will be taking so many values from the table that sometimes it might get a bit confusing. So this is a very good way to organize our what the values we have and don't have. Okay, we know our saturation temperature is 91.76 degrees Celsius. Our P1 is 75 kilopascal. P2 is 3 megapascal. P2 is equals to P3 at 3 megapascal. T2 we don't know. T3 we are given at 350 degrees Celsius. P4 we know it is at 75 kilopascal because P4 equals to P1. Okay. Then we need to understand what is our goal. The goal is to find the thermal efficiency of the cycle. What is the formula for thermal efficiency? Let me write over here that NTH equals to 1 minus Q out over Q in, which is basically Q out is H4 minus H1, which is the condenser where heat is rejected from the system. Meanwhile, Q in is the boiler at H3 minus H1 where heat is added into the system. Okay. So therefore we will get H4 minus H1 divided by H3 minus H2. Okay. So our goal is to find H1, H2, H3, H4. Let us determine. Now, I mentioned earlier that we can find H1 and H3 from the table. Let's find that. Table A5, at 75 kilopascal, we can find our HF and also our SF. 384.44 kilojoule per kilogram, and our SF1 will be 1.2132. So let's write it down. Kilojoule per kilogram Kelvin. H1 is 384.44 kilojoule per kilogram. Okay, then we can also find for S3 and H3. Now for S3 and H3, we won't find it from table A5 because this point 3 here is in the superheated region. So any region past at this region here is the superheated region. So superheated region has a different table. Alright, it's at table A6 of your appendix. Search for P equals to 3 megapascal, since it is given that the pressure is 3 megapascal, and then find your saturated temperature at 350 degrees Celsius. After that, we would find that this 3116.1 is our H, 3116.1. Meanwhile, our S is 6.745. So let's put these values, insert it into our table. (6.745 kilojoule per kilogram Kelvin). Meanwhile, H3 will be 3116.1 kilojoule per kilogram. Okay, next we need to find our H2 and H4, since these are the only values that we do not have. So for us to solve H2, there is a hint. Usually when we determine the work equation, we will write W equals to delta P multiplied by V, right? And usually our unit for delta P will be in kilopascal, our unit for V will be in meter cube. However, we are not given the value of the volume in meter cube, but we have been given the specific volume value from the table A5. This is denoted as a small v. So we can rewrite our equation as W in, small w in, equals to delta P multiplied by specific volume, small v. And specific volume's equation is meter cube per kilogram. So to find specific volume, we go to table A5 at 75 kilopascal, over here, VF, saturated liquid VF, 0.001037, and the unit is meter cube per kilogram. We substitute it into this equation here. So delta P will be 3000 kilopascals minus 75. Now we cannot make it into pascal, we have to multiply in terms of kilopascal so that the unit will not be mixed up. And then we multiply specific volume of that we just found from the table of 0.001037 meter cube per kilogram. Therefore, our final value of W in will be 3.033 kilojoule per kilogram. Now, interestingly enough, kilojoule per kilogram is also the unit of H, right? Of enthalpy, H. So, can we make a deduction that we have W in of 3.033 kilojoule per kilogram, and we have it is equal to H2 minus H1. Can we say this? Because we have work in and we also have 2 points over here. So we can say that. Therefore, let's move this down a bit. Oops. Never mind. We can say that we need more space. We can say, continuing, that 3.033 kilojoule per kilogram equals to H2 minus H1. Okay, and we know our H1 value, therefore our H2 will be 3.033 plus H1, and our H1 value is 384.44 kilojoule per kilogram. That's over here, 384.44. Therefore our final value of H2 is 387.47. Oops. 387.47 unit kilojoule per kilogram. Let's throw in here 387.47 kilojoule per kilogram. Okay, now the only thing we are missing now is H4. Once we get H1, H2, H3, H4, we can finally substitute it into our final equation and finish the question. How do we determine H4? Now, I mentioned earlier that we have to use the quality equation. Okay, so this, as you can see in your screen right now, this is the quality equation. S minus SF divided by SFG. We can find this one from the table, we can find this one from the table. We can also change S and change it into H. So H minus HF divided by HFG. We can find HF from the table, HFG from the table. Okay. Do we have S from the table? Yes, because our S3 equals to S4. Okay, great. Do we have H? No, we don't have H. We don't have H4. So we need to find. So our strategy is we need to use this equation to find the value of X. Then we will substitute X to find our value of H from this equation. Okay, don't worry, it's very simple. So let's begin. X equals to S4 minus S4F divided by S4FG. Okay, we can determine S4 from our values that we have gotten here, given that S3 equals to S4, so S4 is 6.745 kilojoule per kilogram Kelvin, 6.745, 6.745 minus, okay, S4F, here, under table A5, we can go for S4F, SFG here, 1.2132 and 6.2426. okay, so our value of S4F is 1.2132 that we just determined from the table, and S4FG is 6.2426 that we just determined from the table as well. Our X value, our quality value, is then 0.8861. Great. Now we take our x value of 0.8861, we make it equal to H4 minus H4F divided by H4FG. We can determine H4F and H4FG from the table. Let's go. H4F and H4FG. H4F is 384.44 and H4FG is 2278. Okay. H4 minus H4F is 384.44 divided by HFG, which is 2278, and this is quality 0.8861. So with a bit of multiplication and arithmetic, you would get H4S 2402.98 kilojoule per kilogram. Okay. Just for reference, HFG is actually HG minus HF. So if you look in this table, if you might be wondering, what is, let's just say you have HFG. HFG is basically 2662.4 Hg minus HF 384.44. Okay, let's move back and remove this notation. 2402.98. Let's put it back into our summary table. Okay, summary table 2402.98. Kilojoule per kilogram. Okay, excuse my handwriting, not my best day. So we finally have determined H1, H2, H3, and H4. Now we can substitute all these values into our efficiency equation that we've derived earlier, so that we had an idea what we needed to do. H4 minus H1 divided by H3 minus H2. Two four 2402.98 minus H1 of 384.44 divided by 3116.1 minus H2 of 387.47. Our final answer will be 0.2602, and this is now equivalent to 26.02%. So this is our final answer. Okay, let's review what we have done before we summarize this question. We have 3 megapascal, 350 degrees Celsius. We have noted it over here. 3 megapascal, 350 degrees. After that, we know the question says it's 75 kilopascal at the condenser. After that, we have determined from point 1 is the T saturation. We have determined from table A5 as 91.76. After that, we have written down in our summary table like this. You see, you don't have to completely determine everything. There are some gaps here and gaps here because they're not relevant to the question, but it's still good practice because when you go to the next few questions, and you will have until T5 and T6, or even T4S or T2A, and all these different variations. So it is good to have it in order so that you don't get confused or you don't get mixed up. Okay, so we determine the value of H1 from the table, we determine H3 from the table, we determine H2 from this equation here. W equals to delta P multiplied by specific volume V. So we have determined H2 as 387.47. After that, for H4, we determine the quality. Quality was determined using the values from the entropy to find the quality of 0.8861. And after that, we use 0.8861 to find our H4. Okay, once we have our H1, H2, H3, H4, we determine that the efficiency equation is NTH equals to 1 minus Q out over Q in, which is equivalent to H4 minus H1 divided by H3 minus H2, based on this graph over here. H4 minus H1 is Q out, and Q in is H3 minus H2. After that, we determine it to be 0.2602, and finally that equals to 26.02%. So that is what we have done just now. Thank you very much.